In this video, we are going to talk about the topology of the real numbers, which includes discussions about a neighborhood, open and closed sets, and then accumulation points and closures. We will go through these topics with many examples and proofs, and at the very end of this video, there are some example problems for you to try. We'll start with the definition of a neighborhood. Let x be a real number and epsilon greater than 0. A neighborhood of x, denoted with this n x colon epsilon, is all the real numbers y such that the distance between x and y is less than epsilon. So this is our x. Everything here between x minus epsilon and x plus epsilon, everything in between, not including the endpoints, so this is a strictly less than, so not including the endpoints, would be in the neighborhood. In two dimensions, which we will not be dealing with, but maybe you'll deal with this in things like complex analysis. If you have a point x, the neighborhood of x is all the points surrounding x such that the distance between x and the other points in the neighborhood is less than epsilon. So it's kind of this disk, everything inside this open disk. Our two examples which we have just mentioned, if we have a neighborhood of x of radius epsilon, then that will be the open interval that we have drawn here, x minus epsilon to x plus epsilon, and it's the open interval does not include the endpoints. And then we talked about the two-dimensional. A neighborhood of a point is a circle of radius epsilon. Next, we have the definition of a deleted neighborhood. So x is a real number, we have epsilon greater than 0. A deleted neighborhood of x is the set of the form, and we denote this with an asterisk, and it's the y in the real numbers such that the distance between x and y is between 0 and epsilon. In effect, this 0 here excludes the possibility of including x. So the deleted neighborhood of x epsilon is the same with it's the same neighborhood as before, except now we're excluding x. So it's the neighborhood with the relative complement of the set x. Our next definition is an interior point of a set S. So let S be a subset of the real numbers. So here we have the real number line, and then I have S as a subset, and I made this an open interval. It could actually be closed. If you wanted, you could include the endpoints. A point X in R on the real number line is an interior point of the set S if there exists a neighborhood N of X such that N is a subset of S. So in other words, X is an interior point if there is a neighborhood, and it can be a tiny neighborhood, but there's a little area, space around X that is totally contained inside of S. So I can see that X1 is an interior point of S. Now I have another point, X2, very close to this end of the interval, but not quite. It's not at the end, but it's close to. So I can still draw a very tiny neighborhood. It has a small epsilon, a small radius, inside that is completely inside S. So X1 and X2 are both interior points. X2, I had to choose a much smaller epsilon in order to get the neighborhood completely contained in S. But that's okay. It is still an interior point. Now let's look at, and in this case, remember, we are in an open interval, and let's say X is at the end point of our open interval. So there's no small neighborhood that can be totally contained in S because X is right at the endpoint. So I can't draw something around it that'll all be contained in S. So in this point, this X is not an interior point. This point X that is at the end of the interval, of the open interval, is called a boundary point. And here is the formal definition of a boundary point, that when you look at a neighborhood with a small epsilon, and a part of it will intersect S. In other words, the intersection of the neighborhood and S is non-empty. So part of this neighborhood will intersect S. And the second condition is that part of the neighborhood will intersect R minus S, the complement RS, and that again is everything outside this interval. So the neighborhood will also intersect R minus S. And if it intersects both S and R minus S, it is considered a boundary point because it's on the boundary, so part of it will be inside of S, part of it will be outside. I have a note here. If X is a member of S, then every neighborhood of X will have a non-empty intersection with S. I have a little example drawn here. So I have the open interval between 0 and 5. So 0 is a boundary of this interval because any neighborhood will contain things inside this interval, and it'll also contain points outside the interval. And 5 is also a boundary of S. Then I can have an interior point X that is located X units from 0, or 5 minus X units from 5. So our next example uses this drawing. We're looking at the open interval 0 to 5. We're going to let X be an element of S, and we want to show that X is an interior point of S. So if we choose epsilon, the minimum of X, and 5 minus X, the minimum of these two, then we claim that the neighborhood X epsilon is a subset of S, which would make X an interior point. And remember, we're only talking about X being an element of S, not stuff outside of S. And a quick example how this epsilon would work. So if we're considering the point X equals 3, epsilon is the min between 3 and 5 minus 3, which is 2. So that would equal 2. So that means around X, we could look at a diameter of 2. So it goes from X minus 2, which is 1, X plus 2, which is 5, not including the endpoints. So this diameter of 2 will give us a neighborhood totally contained in the set S, and therefore X equals 3 would be an interior point. So here we've done this for X equals 3, and we want to show that this is true for all, we want to show that X, it'll be true for X if we take epsilon to be the minimum of X and 5 minus X. So looking at our definition of our neighborhood for all y in our neighborhood, and X is between 0 and 5, we have the distance between y minus X is less than epsilon. So getting rid of the absolute values, we have y minus X is between epsilon and negative epsilon. If we're looking at y minus X being positive, then we're on kind of in this area. So that'll be less than or equal to our 5 minus X. And if we're looking at y minus X being negative, we're in this area. So our epsilon is going to be less than or equal to X. So this is this statement here. This is what our neighborhood looks like. So given a value X equals 3, I can tell you what my neighborhood is going to look like. So I'll plug it into my formula. Y minus 3 is less than 5 minus X and is greater than 3. So my Y, my neighborhood, is going to be between 0 and 2, which is exactly what we had drawn over here. So this is just, these calculations, this drawing is just to show you that we can find a neighborhood using this epsilon. And for different values of X, I've calculated the different epsilons over here. Remember, X cannot be 0 or 5. And we can see that every point in S is going to be an interior point of S. And we denote interior with this int. Interior of S is equal to S. Our next example, let S be the closed interval 0 to 5. The point 0 is a boundary point of S because every neighborhood is going to contain some points less than 0. It's going to contain points not in S. In this example, the interior points is the open interval 0 to 5. So the interior points do not include 0 or 5. 0 and 5 are the two boundary points. The reason why the interior points is open is because once you get to the endpoint 5 or the endpoint 0, any neighborhood you draw around it will contain points either greater than 5 if you're over here, or if you're trying to draw a neighborhood around 0, all the neighborhoods will contain something less than 0, something outside of S. So neither 0 nor 5 are part of the interior points, which is why this is open. Then why are they boundary points? Well, let's just look at 5 as our example. So any neighborhood of 5 is going to have a non-empty intersection with S. In other words, it will contain points in S, and it will also contain points outside of S. In other words, it'll have a non-empty intersection with R minus S. The same can be true of 0. And something important about this is that S, being a closed interval, contains its boundary points. And the same could be said for any closed interval. 3 examples. Let S be the half open interval 0 to 5. What are the interior points? What are the boundary points? Let S be the interval 2 to infinity, half open. What are the interior points? What are the boundary points? And let S equals R. What are the interior points of S? And what are the boundary points? The interior points is the open interval 0 to 5. And so we do not include 0 because any neighborhood of 0 will include things outside of 5. So 0 is not in the interior, which is why it's an open interval. And of course 5 is not in the interior because 5 isn't even in S. 0 and 5 are both boundary points because any interval around 0 is going to contain things outside of S and inside of S. Similarly for 5. Any interval that you draw around 5 is going to contain points inside of S and points outside of S. Here we have the interval from 2, including 2, to infinity. So the interior is 0 to infinity. It does not include the point 2 because any interval around 2, any neighborhood around 2, will contain elements less than 2, which is not inside S. And then the interior goes all the way through infinity. The boundary point is equal to 2 because any neighborhood containing 2 contains points inside of S and points outside of S. And then infinity, since it keeps going to infinity, the infinity is not a boundary because it doesn't contain points outside of infinity. And then finally, let S equals R. The interior point is equal to S. So if we take the entire real number line, any real number, we can always then take a small interval around any real number and it will be contained inside R, which is why the interior is considered all of S. And the boundary, well, there's no boundary because once you take an interval around around a real number, it will contain elements inside of R, but it won't contain elements outside of R, which is why the boundary is equal to null. Here is another example. Let S equal the open interval 1 to 2, union the half open interval 2 to 3. Find the interior of S and the boundary of S. I drew this in S, so I have the open interval 1 to 2, and then a union with the open interval 2 to 3. So the interior points here is the open interval 0 to 2, and again it won't include 1 or 2 because 1 and 2 aren't even in S. And then it will go from 2, not including 2 because again 2 is not part of S, up to but not including 3. And 3 is not included because if we draw a little neighborhood around 3, we'll definitely can have elements that are outside S, greater than 3, and so it is not considered interior. So we leave off 3, so we keep this as an open interval. The boundaries then are 1, because once we draw a little circle around 1, we have elements outside of S and elements inside of S. 2, because if we draw a little tiny neighborhood around 2, well, 2 is not in S, but the moment you have a little epsilon around it, you're going to be inside S on this side as well as in S over on this side. So 2 is on the boundary. Similarly, 3 is on the boundary because once you draw a neighborhood around 3, you'll have things inside of S and things outside of S. So there are 3 boundary points. And now we can formally define open sets and closed sets. So you know what these are because you've been drawing these open intervals and closed intervals since you are in 5th grade or 3rd grade, whatever. But we have the formal definition. Let S be a subset of real numbers. If the boundary of S is contained in S, then S is said to be closed. If the boundary of S is contained in R minus S, then S is said to be open. And again, this is consistent with the intervals you'd seen in R1. Since 1, 2 is open, since S does not contain its boundary points, S prime is equal to the closed interval 1, 2. S prime contains its boundary points. We have a theorem. A set S is open if and only if S is equal to the interior of S. And again, if you draw your open intervals, intuitively this makes sense. Equivalently, S is open if and only if every point in S is an interior point of S. A set is closed if and only if its complement, R minus S, is open. Here's the theorem I just gave you without proof. I also just put the definition of interior point of S. I kind of copied it here so you'd have it, I don't know, to remind you as notes. And then we're looking at these two intervals, the open interval 1, 2 and the closed interval 1, 2. If I look at the open interval 1, 2, the interior is equal to 1, 2. Again, 1 is not even in S, 2 is not even in S, so yeah, the interior has to be 1, 2. The boundary is equal to 1, 2 because if you look at 1, any neighborhood of 1 will contain points in S. It'll also contain points outside of S. Similarly for 2. Then we look at the closed interval. Now the interior is still 1, 2. 1 is not part of the interior because any neighborhood around 1 will contain points outside of S. So it has to be the open interval. But for this reason, 1 is part of the boundary, and similarly 2, any neighborhood around 2 contains points inside of S, not outside of S. So 1, 2 is in the boundary. So let's look at that and compare it to our definition and our theorem. And just a quick note, when I was saying what was interior and what was the boundary, I was using this definition here of interior points, and it was in terms of neighborhoods. So first we'll look at this definition of open and closed set. If the boundary is contained in S, then S is closed. Otherwise, it's open. So let's look at this set here. Does S contain its boundaries 1 and 2? And it does not, because S is open. So we consider this an open set. So here, the boundary is 1, 2. In this case, S does include the points 1 and 2. So by this definition, S is closed. Second, let's look at this theorem. A set is open if and only if S is equal to the interior of S. Well, here's interior, here's S, and they are equal, and it is open. A set is closed if and only if the complement of S is open. So in this case, we're going to have to look at the complement of S, which will look like this and like this, and it would be open. So that would mean, by this definition, S is closed. And again, I haven't proven anything. I'm just giving you an example to illustrate what this definition and this theorem are saying. I will also say that this theorem comes in useful for proofs later, so it is worth knowing or writing down. Actually, it's worth knowing. And here are 4 quick examples for you. The last 2 are kind of interesting. So the interval 0 to 5 is open, and the interval here, 0 to 5, is closed. So it's totally what you expect with your interval notation from 3rd grade. Any neighborhood is an open set since it is an open interval. 0, 5, this half open interval is neither open nor closed. I guess I just called it half open, but anyway. And then similarly, the closed 2 up to infinity open is considered closed. So infinity would give you something closed. The entire set of real numbers is both open because the interior of R is equal to R, and closed since it contains its boundary. And last, is the empty set open or is it closed? And it is both, since the interior is equal to the null set, and closed since the boundary is the null set and the null set is contained in the null set. We have another theorem. The union of any collection of open sets is an open set. and the intersection of any finite collection of open sets is an open set. I have a little drawing here just to kind of get it in my head what's going on. You have a bunch of open sets and you're going to union them. We're going to start with the union. So let the script A be an arbitrary collection of open sets, and let S be the union of the sets A, if A is a member of our collection of open sets. So the union of these sets. And we're going to do this proof by showing every point in S in this union is an interior point. And in doing so, we're using this theorem here that S is equal to the interior of S. Everything is in the interior. And we will start with let X be a member of S. Since X is in S, then X must be a member of one of the sets A. Let's call it A sub 1. Since A sub 1 is open, then X is an interior point of A1. Therefore, there's a neighborhood of X that is a subset of A1, and that same neighborhood that it inherits from A1 is a neighborhood in the subset S. Hence, S is open. Next, we'll look at part B, the intersection. So let A1, A2 up to AN be a finite collection of open sets, and let T be the intersection of these sets. We will consider two cases, one that T is empty, and T is not the empty set. So first, if T is the empty set, we're done, since the empty set is open. It's also closed, by the way, but it is in particular open. If T is not the empty set, let X be in T. Then X is a member of A sub I for all the A sub i's, since it's in the intersection. So in other words, let's just say A1 looks like this and A2 looks like this. We're looking at the intersection, so we kind of are in between this green and blue parentheses. And let's say we have our X inside the intersection. Of course, there can be many more sets, like there could be an A3, A4, but I just wanted to make mine simple, so I only considered two sets, A1 and A2. Since each A sub I is open, there exist neighborhoods N sub I, such that N sub I is a subset of A sub I. So in other words, here I have in A1, which is in blue, I can have a pretty big neighborhood here around X that is totally inside A1. And it's totally inside A1 because it is open. A1 is open. A2, X is a little closer to this, the end of the interval. So the neighborhood has a much smaller radius, but that's okay. I can still, since A2 is open, I'm guaranteed to be able to have a neighborhood that's completely contained in A2. So we will have two neighborhoods with two different radius. A2 will have to be small. A1 could be a little bit bigger. The radius could be a little bit bigger, but A2 needs to be kind of small. Now we're going to take our epsilon to be the minimum of all the epsilons of the A sub n. So in this case, our epsilon is going to be the epsilon for A2, since A2 needs to be smaller. Then, this neighborhood is a subset for all the A sub i's. Thus, X is an interior point of T, and T is also open. Our next example, for each n in the natural numbers, we're going to consider the set AN that goes from -1 over n to 1 over n. Then each AN is an open set, and by our theorem, the union will be an open set. But now what we want to know is the intersection an open set? Since this theorem does not apply because that's only for a finite collection of open sets. Just to get a feel for what was going on, I wrote out what A1 was, is just -1 to 1. A2 is -1/2 to 1/2. A3 is -1/3 to 1/3. A4, -1/4 to 1/4. And I drew the intervals A1, A2, and A4 over here, and I didn't do A3 just because. But you can kind of get a sense that as n goes, you're closing in on the 0, which is what I have written here. As we intersect everything, the intersection is going to be this 0. And then we can see each AN is an open set, but the intersection is equal to 0, which is not open. A single point can't be open because there's no neighborhood of 0 that any neighborhood is going to contain stuff outside of 0. So this set is not open. Thus, we see the restriction of the last theorem. It has to be a finite collection of open sets. Here we had infinitely open sets. And here we have an example. Find a collection of closed sets whose union is not closed. Remember, our theorem here, when we're talking about union, is open sets. So we want an example of closed sets whose union is not closed. To find an example, I'm going to borrow from this last example. And in particular, I'm going to look at this 1 over n. Because what happened with 1 over n, as n got large, it approached 0, but it never actually took that value. And so that's going to be what we exploit to give us our open set, something that approaches 0 but never quite reaches it. In particular, I'm going to change this an to be 1 over n to 2, and this will be my closed interval. So you can see a1 is 1, 2, a2 is 1/2, 2, a3 is 1/3, 2, a4 is 1/4, 2. So you can see the union is going to approach 0, but it will never reach 0. And of course, on this other side, the right-hand side, I get to include up to 2. But by setting the left-hand side equal to 1 over n, that is what will do it for me. It will not be a closed set. The union is not closed. This next example, prove the open interval AB is open. A and B are real numbers with A less than B. And, I always just read this with the parentheses and say, well, it's open because, it has these parentheses and not the brackets. But let's do a proof. And what we need to show using our definitions is that for any x, or for all x in the interval AB, x is in the interior of AB. In other words, there's a neighborhood, x, with some epsilon that is in the interval AB. And this is sort of like that earlier example where we're looking at the interval 0, 5. So we're going to let x be a member or in the interval AB, and we want an epsilon less than the minimum of the distance from x to A and x to B. So here we have epsilon is less than a minimum of absolute value x minus A, absolute value x minus B, and we could, since we want x to be less than the minimum, we could try subtracting a value, but we don't want to subtract something so much that we end up outside the interval. So really the safe thing to do, or actually really the only thing we should do, is we need to divide this minimum by some number. And 2 will do. I mean, you could have done 1/10, and that would have been fine. But we're just going to divide by 1/2 here, and that will be our solution. But any fraction less than 1 here would have been fine. The next topic is of accumulation points. We'll look at the definition. If S is a subset of real numbers, a point X in the real numbers is an accumulation point, also called a limit point or a cluster point of S, if every deleted neighborhood of X contains a point of S. That is, for every epsilon greater than 0, the deleted neighborhood of X has an intersection with S. We will do some examples of this and also an example of points that are not accumulation points, and it will become more clear. And the set of all accumulation points of S is denoted with the S prime. And if X is an S and not an S prime, then X is called an isolated point. So isolated point is sort of intuitively what you would think. It kind of gets away from S, so it's isolated itself away from S. Whereas an accumulation point can't get away. And in fact, no matter how close you want it, no matter how small the epsilon is, there's always something in the neighborhood, no matter how small, that overlaps with S. So in other words, you can get arbitrarily close to S if it is an accumulation or a limit point. So our first example, if S is the half-open interval, 0, 1, then what is S prime, the set of accumulation points? If we consider some point, x1, sort of in the middle of the interval, then every deleted neighborhood of x1, and remember the deleted neighborhood is a neighborhood around x1 where you actually delete then x1. So it's all the points around x1, not including x1. So you can see every neighborhood of x1, no matter how small or how big, is going to contain elements in S. And that's what I have written here. Every deleted neighborhood of x1 contains a point of S. And the middle points are clearly accumulation points. We consider the point x equals 1. So every neighborhood around x equals 1 is going to contain some points that are less than 1. And hence, every deleted neighborhood has points in S. And 1 is an accumulation point. Now if we consider x equals 0, every deleted neighborhood, so any little neighborhood here that we take out 0, still contains points that are greater than 0. So that means it will contain points in the interval S, and therefore 0 is also an accumulation point. So the accumulation point are all the points in the middle, including the endpoints. So here is S prime, the set of accumulation points. In contrast, let's look at the point 3. So here's our S1, our interval from 0 to 1. And then we have this point out here that gets away from the set. If we look at a neighborhood around 3, I mean, there are some neighborhoods that include S, but if we take a small enough neighborhood, you will see that we delete X from this neighborhood and there's no intersection with S. So 3 would be considered an isolated point. In this way, I think of the isolated points as points that get away. They can isolate themselves from the set S, whereas the accumulation points cannot get away from the set. Even 0, which is not in the set, it can't really get too far away from the set because you can choose an epsilon really small, and because it is an accumulation point, any neighborhood you draw around 0, no matter how tiny the epsilon, will always intersect S. So in other words, the points in S are getting arbitrarily close to this limit point or accumulation point. So we've done this example here where the interval is the half-open interval 0 to 1, and we said the set of accumulation points is the closed interval 0 to 1. So now let's consider S, which is equal to 1 over n. N is a natural number. What is S prime? I can write out some elements of S. I have 1, 1/2, 1/3, 1/4, etc. So these are discrete points. And now I can ask, what are my accumulation points? So first I'm going to look at X in the middle. So consider X equals 1/3. Does every deleted neighborhood of X equals 1/3 contain an element in S? And the answer is no, because I blew up this picture here. If I have 1/3, I can take an element, a neighborhood that doesn't hit 1/4 and doesn't hit 1/2, so right in the middle, a small enough neighborhood. And when we consider the deleted neighborhood, so when we take out X equals 1/3, there are no elements of S in this neighborhood, in the deleted neighborhood. So the points in the middle are not accumulation points. Because they have some space around each of the points in S, each point has an opportunity to get away from S, if only for just a little bit. And in fact, the distance we would need to have a deleted neighborhood which contains no element of S is this distance is shorter than this distance, so it's 1/3 minus 1/4. And then you can see that the elements of S do get closer together as n gets large and the series gets close to 0. Now we can consider X equals 0. And as I said, the elements of S are very close together by the time we get to 0. And in fact, they're arbitrarily close, meaning no matter how small of an epsilon you choose, there will be some element, 1 over n, in the deleted neighborhood of 0. So any deleted neighborhood of 0 will contain elements of S because the elements of S are getting super packed in. So 0 is an accumulation point. We can see 1, obviously we can draw this huge, anything up to 1/2. Any epsilon up to 1/2. 1 will be isolated. So the only accumulation point of this S here is 0. The next example, if S is equal to the set of natural numbers, what is the set of accumulation points? Here you can see each natural number, we can draw a neighborhood as long as the neighborhood has an epsilon less than 1. You can see that every deleted neighborhood will miss all the other elements of the natural numbers. So here I just chose epsilon equals 1/2. So for any x in the natural numbers, the deleted neighborhood with epsilon equals 1/2 contains no elements of s, and therefore there are no accumulation points. And I've written that here as prime is the empty set, and all points in N are considered isolated points. The next example, if S is a finite set, what is the set of accumulation points? As long as the set is finite, there's always space between the members of S. It's not dense like the real numbers. So for example, let's let S equal x1, x2 up to xn, and I just drew an x1, x2, and x3. I just put in 3 elements for simplicity. And let's say we're looking for an element y in the real numbers and asking, is this an accumulation point? And what we can do is look at y and compare the distance between y and each of the x sub i's. In this case, y is closest to x2, so we can take y minus x2, and then as long as epsilon is less than the distance between x2 and y, or x sub I and y, then that epsilon will work as a neighborhood for our deleted neighborhood, such that the intersection is the empty set. So again, as long as here, if we take our distance for our radius of our deleted neighborhood is going to be less than x2 minus xy, once we delete y, we have no elements of our finite set. Thus, y is not an accumulation point of x. And since y was chosen to be an arbitrary real number, that means there are no accumulation points. S prime is empty. Now that we have the definition of accumulation points and isolated points, we can talk about the closure. So let S be a subset of the real numbers. Then the closure of S, denoted CL of S, is defined as S union its accumulation points. So point X is in the closure if and only if every neighborhood of X intersects S. I have found this second characterization sometimes helpful in proofs. So let's look back at that example with a half open interval 0 to 1, where we said the set of accumulation points would now include 0, and the reason is every deleted neighborhood of 0 would have an intersection with S, because every deleted neighborhood of 0 has some elements a little bit greater than 0. So the S prime then would pick up this 0, and it sort of closes our set, so that our S prime, our set of accumulation points, along with S, will now give us a closed interval. And we can see that the point X is in the closure if and only every neighborhood of X intersects S. And that's true at the endpoints as well. We have this theorem, let S be a subset of real numbers, then S is closed if and only if S contains all of its accumulation points. The closure of S is a closed set, and S is closed if and only if S is equal to its closure, and the closure of S is equal to S union the boundary of S. To make room for my proof, I summarized the definitions and theorems that I wanted to make use of to reference over here. I have my theorem, I made it a little more space compact, and then I'm going to start by proving part A in the forward direction. The forward direction of part A would be S is closed will imply S contains all of its accumulation points. So I'm going to start by assuming S is closed, and then I'll say let X be an accumulation point. So X is in the set of accumulation points. And then I want to show that S contains all of its accumulation points. That is, if X is in the accumulation points, X is also in S. I'm going to do this by contradiction, so that I'm going to start by assuming X is not in S. If X is not in S, then X is in the open set R relative complement of S. So I have drawn this here. Since S is closed, that must be R relative complement of S is open. For this next statement, I used this theorem that said a set S is open if and only if S is equal to its interior. So that means if X is in this open set R relative complement of S, that means X is in the interior of all R relative complement of S. To be an interior point, that means there's a neighborhood that is totally contained in the set. So to be in the interior of R relative complement of S, that means there's a neighborhood that is completely contained in R relative complement of S. So for this step here, I used both this theorem, part A, as well as the definition of what it is to be an interior point. This neighborhood here then does not intersect S, but this contradicts the fact that X is an accumulation point of S. In other words, to be an accumulation point, every deleted neighborhood must contain a point of S, but in this case it does not. So because this is a contradiction, it must be our assumption was incorrect. And here I have, since our assumption is not correct, that must mean that X is in S. Here I put the shortened version of the proof that's in your book for your reference. I also put the theorem that we use to prove the forward direction of part A, because we're going to use that also in the other direction, part A. And the other direction of part A is to assume that S contains all of its accumulation points, that is, S prime is a subset of S, and we want to show that S is closed. To show S is closed, we are going to use this theorem again that says a set is closed if and only if its complement R complement S is open. So we are going to do that. We're going to show the complement R complement S is open. So we're going to let X be an R complement S. The next point is X is not an accumulation point of S. That is, we can get as close as we want to S, not including the boundary since S is closed, but we can get as close as we want to S and then find an infinitesimally small epsilon. We will then use that epsilon to make our deleted neighborhood, and we'll see that deleted neighborhood will not contain any points from S. This here implies that X is an interior point by definition of interior point, and then by this theorem that says that a set is open if it's equal to its interior, well, since X is any point in R relative complement of S, that means R relative complement of S is open. Next, we'll do the proof of part B. The closure of S is a closed set. And this proof, it's useful when doing one of the other proofs in the review exercises. We will start by noting from part A, it is enough to show that if X is in the accumulation of the closure of S, then X will be in the closure of S, because part A says S is closed if and only if S contains all of its accumulation points. So it's closed if it contains all of its accumulation points. We will start with X being an accumulation point of the closure of S here. So looking at the definition of an accumulation point, that means every deleted neighborhood of X contains a point in the closure of S. I mean, here it says S because that's talking about an accumulation point of S. But here we have an accumulation point of the closure of S, so that means every deleted neighborhood of X contains a point of the closure of S. I wrote this out symbolically, so I wanted to say that every deleted neighborhood of X, so to talk about every deleted neighborhood of X, that's for every possible epsilon, right? So these are the deleted neighborhoods, all of them are the different epsilons. And for every deleted neighborhood, it contains a point in the closure of S. So that means there's an intersection with the closure of S. So if Y is in the deleted neighborhood, it's also in the closure of S because it contains a point in the closure of S. So that's how I rewrote this symbolically. And then I substituted for closure of S union S prime. So here I have that Y is in the deleted neighborhood intersected with S union S prime, which means there are two cases. Either Y is in the deleted neighborhood and in S, or Y is in the deleted neighborhood and in S prime. Because this proof was a little difficult, I want to remind myself what it is I'm trying to show, which is X is in the closure of S. And according to this definition, X is in the closure of S if and only if every neighborhood of X intersects S. So again, I want every neighborhood of X. So all possible epsilons, so all possible neighborhoods intersected with S is not equal to 0, is not empty. I am going to take a look at my Y that is in my deleted neighborhood of X. So here I have a neighborhood of X with X taken out. That was kind of an open circle here. So this is my deleted neighborhood, and I have a Y in the middle of it, and because this is open, I can make a little neighborhood around Y itself, and I'll call its radius delta. And here I've written this out. So for this Y over here, that's in the deleted neighborhood, also in the closure of S, there's a neighborhood around Y with a radius of delta that is completely contained in the deleted neighborhood of X. But since Y is in the closure of S, that means every neighborhood of Y, according to this condition here, will intersect S. That is, there exists a Z in the neighborhood of Y that's also in S. Now I have Z in this neighborhood of Y, which is a subset of the deleted neighborhood of X. So I have Z in the deleted neighborhood of X and also in S, which is exactly what I needed to show, that the neighborhood of X and intersect with S is not empty. Next I have the proof of part C, and I wouldn't have done this, but because B was kind of complicated, C is fairly straightforward, so I wanted to show a more straightforward proof as well. And we're going to show that S is closed if and only if S is equal to the closure of S. We will do the forward direction first, assuming S is closed. We're going to show that S is equal to the closure of S, and this equality has two parts. The first is S is a subset of the closure of S. The second is the closure of S is a subset of S. And for S is a subset of the closure of S, we're going to let X equal to S, and then by definition of closure, since the closure is equal to S union S, X is in the closure. So that one is already done. For the second part, if X is in the closure of S, that means X is in S union S bar. So either X is in S or X is in S bar. If X is in S, then we are done. If X is in S bar, since S is closed, that means S bar is a subset of S, which means that X is in S. The forward direction is done, so we'll do the opposite direction. We'll assume S is equal to the closure of S and show that S is closed. But we have already proved in part B that the closure of S is closed, and since S is equal to the closure of S, it must follow that S is also closed. So this proof was much easier. Now we have gone over our main topics of neighborhood, open and closed sets, as well as accumulation and closure. So next we have some problems for review. Here are 4 problems for you to try. Pause the video, give them a try, and then I'll have solutions on the next slides. And by the way, this proof number 18 is much easier than the proof of part B over here. Here is the solution for the first problem. This is the proof to the next problem. Here is the proof to the second problem. It is fairly straightforward. That's it for this video. Thank you for watching.